We learnt about industrial revolutions. There have been 4 industrial revolutions. We are going through the 4th one right now. We learnt how various technologies have driven various industrial revolutions, and how additive manufacturing is driving industrial revolution 4. How rapid manufacturing has been done using additive manufacturing, how Internet of Things is connected to AM, how digital twins are being developed, and why they are required for better control of processes and better functionality of our newer products. We went through the history of additive manufacturing starting from 1970s to the current state in 20s. Starting from 1971, Johannes Gottwald patented the liquid metal recorder, which is like a continuous inkjet metal printing process. 1980s, Hideo Kodama invented additive methods for photo hardening thermoset polymers. Chuck Hull filed a patent in 1983-84 and also started a company called 3D Systems Corporation, and SLA-1 was released. In 1988, Scott Crump developed FDM and started a company called Stratasys. Stratasys commercialized the first FDM technology. Richard Helsinki patented a method for constructing 3-dimensional articles by particle deposition. This was inkjet technology. In 1980s to 1990, where the 3D printing was actually started, it saw evolution of key additive manufacturing technologies, for example, stereolithography, FDM, and inkjet based methods. In 1993, Emanuel Sachs introduced powder bed 3D printing with inkjet print heads at MIT. A company, Sanders prototype, was started. Later on it was called Solidscape. They began inkjet 3D printing with soluble support structures. In 95, Fraunhofer Society developed the selective laser melting process. 2009 saw the expiration of FDM patents, and which led to commercialization of FDM printers, and now AM was increasingly became integrated with other manufacturing processes. AM was increasingly used for making non-conforming parts, complicated geometries. Further applications of AM was seen, for example, in fuel efficiency in jet engines. Overall, AM process itself was increasingly made more efficient, less material wastage, and more integrated technologies. AM was integrated in aerospace. Airbus and Pratt & Whitney were first end users of it, and it was adopted considerably across many other industries. In 2010 to 20s, AM saw rapid advancements in form of integration. For example, integrated parts in aviation, automotive, and defense. AM was used increasingly for complex geometries to optimize designs and reduce waste. AM by end of 20s had become established manufacturing methods for many key components. This was the period when application of digital twin was also started in the area of additive manufacturing. 20s are seeing versatile applications and advancements in additive manufacturing technology. This technology has now become more affordable. It has diverse applications, for example, in medicine, architecture, fashion, and art. It has seen many technological advancements in terms of software, better slicing algorithms, advanced materials are being used. It is now integrated with Industry 4, and also cyber physical systems around additive manufacturing are being developed. We have seen various applications where additive manufacturing is used for customization and personalization. Various accessories which are customer need based are being developed. Additive manufacturing has now been introduced in education for skill development at various levels. It is part of engineering education. Various short courses and professional courses are available across various domains via various sources. 3D printing has been integrated for better design and prototyping skill. Additive manufacturing offers sustainability and eco-friendly practices. It offers better material usage, more efficient material usage. It reduces waste, and research is going on to further use the recycled material without compromising the property of the final parts. There have been many medical breakthroughs. For example, patient specific implants can be made, tissues can be printed specific to patients, and drugs, medicines can be printed using additive manufacturing. Due to more availability of additive manufacturing systems, the localized production is happening, and which has disrupted global supply chains, and it has changed the overall manufacturing dynamics of even the most complicated parts. There are various value additions by additive manufacturing. As we have learnt, it offers functional performance, it offers customization, it offers superior topology and complex geometry. Weight can be reduced due to new designs, better topology optimization and complex geometries. We can make structures in monolith forms. We do not need to make small parts and assemble them. If there are materials which cannot be machined, they can be made using additive manufacturing. Since using additive manufacturing, parts can be made on demand, it has also solved to some extent supply chain issues. We do not need to keep inventory of materials. We can calculate and estimate definitively how much material is needed, and we do not need to keep inventory of the build parts also. Parts can be printed as needed. We also do not need complicated tools, because even complicated geometries, as mentioned earlier, can be printed in monolith structures using AM. If designs need to be changed or a fresh design is made, it can be immediately printed using additive manufacturing. Since there are not many tools involved other than additive manufacturing machinery, this design change and new design innovations are very cost effective. We have flexible productions, that means we can print as needed and where it is needed. Using conventional processes, it used to take long time, especially for complicated parts. The additive manufacturing technology has reduced design to proof of concept. If a part is obsolete, those parts can also be made simply by scanning those and by applying reverse manufacturing with the help of additive manufacturing. It also offers fast on-ground maintenance, repair and overhaul.
Hello everybody, and now I will take you through the summary of the 4 technologies that I discussed out of the 7 technologies that are listed under the ASTM classification, and I will also try and brief you how you can go about solving the assignment that will be given for this week, right. So, let us get started, and again I would like to go through the definition of additive manufacturing, wherein it is a process where objects are built layer by layer, and this is in stark comparison with say subtractive manufacturing or subtractive manufacturing, like CNC machining, wherein we start with a block of or chunk of material and then we will do some machining to remove material. Here we will add material layer by layer to form a final 3D printed object. And how to add these layers is the data that is known from the CAD model. So, the design file or the CAD data is a very important input into the additive manufacturing. We will be first modeling it in some native CAD software, and then we will convert it into an STL file like you see in the brown part in the second picture. Then we will bring it into an AM software where we will be deciding the orientation in which we want to print the part, as in we want to print it flat or straight, inclined, how we want to print it, we do that orientation decision, and then we will design something called as supports. We discussed support structures also very much in detail. So, these support structures are created in the AM software and then the slicing is done. So, in the red and the green image that you see here, I hope you are able to see the different layers in which the printing will happen. So, this slice file data is transferred to the AM machine, and the AM machine printing process will happen, and after that some support removal or polishing or threading or heat treatment, all of these processes will happen, so that we have the final finished part with us. So, this is how the AM process works, be it polymer or be it metal. There will be two inputs, one is the material and the raw material, the other one is the digital file. These are the two inputs to an additive manufacturing process. In the same machine, you can process different materials when it comes to additive manufacturing. So, with the same FFF printer, you can do ABS, you can do PLA, you can do TPU also. Once the design is ready, you can immediately make a print and check the part or use the part. And now we went through these technologies, right. So, VAT photopolymerization we went through in detail, and if you look at this particular image over here, I think it is a good way to summarize the process. So, what happens in VAT photopolymerization is that there will be a vat, there will be a vessel into which we will be adding a photopolymer resin, and when a laser light or LED light, when it falls on the resin, the polymerization process will happen and the resin is converted into a solid part. All the layers will bind with each other to give a solid 3D part in the end. Like I said, the variations can be that instead of this particular plate moving down as in this picture, it could be that the source of light can be from bottom and the plate can move upwards instead of downwards. So, the advantage if your plate is moving upwards in each layer is that the amount of liquid that you want to print can be less, but the height of the part that you can print can be more. Whereas, if it is like this, then you are restricted by the size of the vat or the vessel. That will be a restriction to the height of the part that you can print. So, few variations, SLA a little slow, DLP more faster. So, each having its own advantage and disadvantage. So, that was vat photopolymerization. The next one is material extrusion, also called as FFF technology, right. Now, in this what happens is the raw material will be in a filament form. However, these days it is possible to have it in pellet form, granule form. So, even these are possible. Basically, when this thermoset kind of a material will pass through the roller and then eventually the hot extruder or hot end or hot nozzle, it will melt, and then this melted material is deposited layer by layer, and then we have the final part that we desire. In this particular technology, like I was saying, is viable for very many different materials, and it is also a very easy and simple process to learn and implement. So, that would be the material extrusion process. Next, we discuss the material jetting process, and like I was saying, it is very similar to our paper printing process, right, or how we print on a paper. And if you see, HP is one of the companies which makes this machine. So, they know the technology very well to make a 3D printer also. They have used the paper printing expertise to do a 3D printing machine. Over here, what will happen is, again the raw material will be in form of a liquid or resin, and this material is jetted out or in a way sprayed out and deposited only where it is required. But very important is that it immediately you have to expose it to UV light, so that the solidification will happen and the shape is retained. Advantage of this particular technology is multicolor parts, just like multicolor printing. You can print with any color, you will get very good accuracy, very good color and very good finish. However, this technology has not been used for production parts till now. So, that was material jetting. Now, moving on to the fourth technology that we discussed, which is the binder jetting technology. Here, what is being jetted out is a binding agent. Only a binding agent will be jetted out, and the raw material. So, whichever material it is that you want to print, it could be sand or it could be metal, this will be deposited layer by layer. So, over here you are seeing the dots which are aligned one after the other. So, please notice that when I zoom in, the powder, sand powder or metal powder, whatever it is, will be deposited one layer at a time, and after one layer of powder is deposited, binder is jetted out only in the regions where we want a solid part. Then again another layer, again binder is jetted out, but after each time the binder is jetted out, there will again be a pass of UV light like you saw in material jetting, which will cause the binder to harden. So, this hardened binder will hold the particles together. Hence, over here the material is not completely solidified. The part that you get out of such an AM machine will not be totally solid. It will not be totally solid. So, it will have something called as a green strength, which is very similar to what we have in powder metallurgy. So, this particular part is called as a green part, and it should be carefully taken out. After carefully taking out the part, we will then do something called as deep powdering, wherein all the excess powder is taken off. Then we do something called as deep binding, where we subject it to a little amount of heat, so that all the binder that has been sprayed is evaporated off, and after that we will put it in a proper sintering furnace where the temperature is raised to, let us say, a metal's melting point, and there the proper solidification of the part will happen. Now, one very interesting thing you should remember in this technology is what? It is that no supports are required while 3D printing it, whereas while sintering maybe some supports are required. So, some of you may be thinking, how will these supports, what are these supports? So, if the area that has to be supported is very simple, you can use some ceramic blocks, pre-formed ceramic blocks. You can just insert it in the debinded part, which is also called as the brown part, and then you can send it for sintering. Or while 3D printing itself, you can print the support, but not attached to the part, right. You can make these simple shapes, and these can be used during sintering. So, these are the 4 technologies that we discussed this week. Going forward, we will be discussing powder bed fusion technology, direct energy deposition and sheet lamination processes. So, in the next week, week number 2, we will discuss these 3 technologies. Yes. Now, again showing some of the variations. So, the assignment for this week is called map the technology, right. There are so many acronyms and variations in the technology that we want to make clear for you, correct. So, what we will do in this particular assignment or assessment is we will give you a name of the process, okay. And this is an example that I have taken here. You will get maybe 10 other acronyms related to additive manufacturing. For example, the question may read only as DOD. So, if you try and find out using the resources that we would have listed, you have to find out what is the full form or the expansion of DOD. Now, the expansion of DOD is drop on demand. So, this will be a multiple choice question. In the assignment paper that you will see, you will find 4 options. Let us say drop on demand or drag on demand or something like that, right. You will have 4 options, out of which only 1 will be correct. So, you have to find out what is the correct name or the expansion of this particular acronym and process given here, which is DOD. The next thing that you have to find out is I have shown 4 categories in this week. So, out of these 4 categories, which technology does DOD fall under? So, for that you need to read up and understand how the process works. You have to read and understand how DOD process works, and when you read, you will realize that a drop of material is delivered where the demand is there, and that is very similar to what we have understood to be material jetting or material jetting technology. Now, again this will be a multiple choice question. So, we would have written MJT, BJT or SLA and FFF. So, I would have given those 4 options, and you have to choose which is the correct ASTM process category that DOD falls into. Now, we will make it a standard to also write something called as a hybrid. Now, there are some processes which can be a combination of, let us say, SLA as well as MJT. Maybe there may be a process which is a combination of let us say FFF and binder jetting, maybe or maybe not, but we will keep that option. So, remember that one of the correct options could also be a hybrid technology or a novel technology, wherein what we have studied, it may never be a part of it, and it may be something very new. So, that time it will be a novel technology. So, other than the process 7 processes that are there, the options will also be hybrid and novel, and then you will know when to choose these 2 options. The next question that we will ask is what is the form of raw material used in the DOD process. So, here we will have options like liquid, powder, filament, pellet or something like that, 4-5 options, and you have to choose which is the correct one. Again, you will know this only when you read and understand how the DOD process works. The last question would be support structure requirement. When you try and print a part using the DED process, you need to let us know if supports are required or not. In case of DOD, because it is falls into the category of MJT, you will have to choose the option of yes. So, your options would probably be yes, no, and we will introduce a third one, because in binder jetting process we said in the AM process there is no support, whereas maybe in the sintering process there will be support, right. So, maybe is something also that we will put up there. So, you will have these 2-3 options and you have to choose the correct one. So, this is how the assignment will look, and this is how you will have to solve it. You would have a list of a reference material, as in we would provide links or sometimes some PDFs. You will have the presentations also for your reference, for you to understand the 7 categories better if you wish. So, you can use this and solve the assignment successfully, I hope. So, I wish you all the best and thank you very much.